Hello, everybody, and thank you for coming for this week's Brown Background seminar. And today we have three presentations. The first presenter is Andrew. He is a third-year AE student interested in electronics programming, astronomy, and spacecraft. He became an electronics hobbyist in high school, and after discovering Dr. Lance's lab 2 years ago, he was given the opportunity to design the GT1 CubeSat electronics. So Andrew, all yours.
All right, thank you. Yes, so the focus of my presentation today is going to be on the GT1 CubeSat avionics system. And specifically, I'm going to be talking about the lessons learned along the development process. So for those of you who don't know what the GT1 mission is, I'd like to give a brief overview of that mission. So here are the GT1 mission goals. Primarily, we want to develop a flight-proven 1U CubeSat bus for future missions to fly various payloads on. And we want to do this with a design to operations mission lifecycle of 2 years. So that means design to delivery in 1 year, with hopefully 6 months of operation time within that 2-year period. We want to demonstrate amateur radio communications between the ground and the satellite. And we also want to train students on all aspects of a space mission. One of the reasons why we're designing a CubeSat bus from scratch instead of buying a off-the-shelf CubeSat bus, so that students can figure out and learn how to design a spacecraft. So this is what a 1U CubeSat bus looks like, and this also happens to be GT1. We have it built up. It's in the Queen bench in our lab. And just to give you a sense of scale, with the solar panels stowed up, the satellite is a 10-centimeter cube in all 3 axes, so it is quite tiny. So what does a 1U CubeSat bus do? It needs to provide structure for mounting the payload, it needs to supply power to that payload, it needs to handle the radio communications between the satellite and ground, and it needs to tell the payload where it is and where it's pointing. And it might provide basic attitude control to be able to spin the spacecraft to a desired orientation for the payload. And it also needs to handle the deployment of the solar panels and radio antenna. And each of these tasks with an asterisk has avionics involved. So you can see that the avionics system is deeply ingrained in the tasks for a 1U CubeSat bus. Okay, so how do we make it in 1 year? This was our overall strategy for GT1. We want to keep the design as simple as possible. We don't want to add any extraneous features to the design. We're trying to make the most simple 1U CubeSat bus that we can. And for choosing our electronics components, we're going to use the method called careful COTS, which I'm going to talk about later on in the presentation. And we're going to rely heavily on environmental testing, specifically vibration testing and thermal vacuum testing, to validate our design so that it'll work in the space environment. And to do this in 1 year, we really need a motivated team and that's willing to work really hard because not a lot of time. So that was the plan, and this is what actually happened. In fall 2019, we started the project by prototyping and starting the design of the flight electronics. And the following semester, we finished the design of the flight electronics and started assembling them. And in fall 2020, we had a completed spacecraft and began environmental testing, vibration and thermal vacuum testing. And hopefully by the end of this semester, we'll be delivering GT1 to the launch provider. Okay, so that was an overview of the GT1 mission, and I'd like to talk about first what worked well for the avionics system. So first up, our choice of flight computer. And for GT1, we chose the Atmega 128 microcontroller, which is very similar to the Atmega 328 microcontroller you would find on an Arduino Uno circuit board, which some of you have probably used in the past. And both of these processors share the AVR architecture, so the Arduino IDE and all the software libraries that work with the Arduino Uno also work with our flight computer, the Atmega 128. And the result of all this is that it's very easy to write acceptance test programs without spending a lot of time configuring your development environment. So this allowed us to write programs on the flight computer very quickly to test various things, and the flight software was easier to write. The next thing is something that I'm calling software tolerance. And this is the principle that there's a chance of the flight software team uploading the wrong program to the flight computer or accidentally having a bug in the software. And you want to make sure that when you're designing the electronics that any program that could possibly be uploaded to the flight computer will not damage the hardware. This is something that I tried to take seriously when designing the electronics so that we didn't accidentally damage the hardware once the satellite was fully integrated. And I have two examples of this, one of which is a design fail that was actually on the GT1 design. And if you can see here in this picture on the left, you see two pins, J1 and J2, and the red lever. And when the solar panels are stowed, you can think of this lever being closed so that J1 and J2 are shorted together. And this deploy SW signal goes directly to the flight computer, one of its I/O pins. And you can imagine that if that I/O pin was configured accidentally as an output and driven high or to the positive supply voltage rail, and the solar panels were stowed, then you'd be shorting the power supply directly to ground, which will destroy the I/O pin, and then your solar panel deployment switch input, may not work anymore. And the solution here is fairly obvious: to put a resistor in series with this deploy SW signal to limit the current. But this is one example of a fail of software tolerance. And the success story is the burn wire demultiplexer circuit on GT1, where GT1 has several of these burn wire deployment mechanisms, which are resistors that melt fishing line, actually, that hold the solar panels in the stowed configuration. And the resistors heat up and melt the wire to deploy the solar panels. But these mechanisms take a lot of power, and if the software accidentally enabled all of them at the same time, then we would overload our power system. So to solve that in hardware, we designed a circuit so that only one burn wire could possibly be turned on at a time. So this way, no matter what software bugs may be uploaded to the flight computer, we don't have any issues on the hardware. All right, the next thing is a functional test program. So the idea behind this is we want a quick and easy way to validate the state of the spacecraft by testing all the basic functionality of every system on the spacecraft. And this is very handy to run before and after every test on the spacecraft and every time you modify the hardware to make sure that everything still works. And this has helped us time and time again on GT1 mission and very useful. And I touched on this earlier about designing the simplest possible 1U CubeSat, and we really took this to heart, designing the minimum viable product of the of the CubeSat bus. So there were no specific performance requirements on our sensors. Our only requirement was to design a 1U CubeSat bus. So because of our time constraints, we decided to design the most basic version of each sensor, which had less design time and minimum testing time required. And this also allows us the opportunity to improve the performance of the sensors in the next iteration of the satellite bus, if that's necessary. Okay, so what parts of the avionics development didn't work, or what gave us problems? Working on the critical systems first. So specifically for GT1, the radio hardware and software development was neglected until late in the mission. This was one of our biggest mistakes, and we made it because really no one on our team had experience with the radio, and it unfortunately naturally happened that was the last thing that we worked on, which was a big mistake. The radio is one of the most critical systems on the spacecraft, and the GT1 radio software and testing is actually holding up delivery of the spacecraft right now. So this is an active problem that we're working on right now. Another thing is the vast amount of cable harnesses inside GT1. So you can see there in the picture on the left just how many cable harnesses we have inside the satellite. And all these cables occupy valuable space inside our small 1U form factor. And they also bring up a chance of human error. You can make a cable harness backwards or upside down and still have it fit in the connector. So some of these cable harness mistakes can be difficult to detect. And once you stake the cable or glue it in place so that it doesn't pop out during vibration, it's very difficult, if not impossible, to disassemble it without cutting the wires. So it's very inconvenient if you run into a problem and need to disassemble the spacecraft. And for these reasons, it's much better to use a board-to-board connector where possible and have it connected mechanically with standoffs and screws rather than glue. And that way you can't make it backwards. It only plugs in one way. Okay, so here are a couple other important points I'd like to talk about the avionics development. The delicate balance of documentation. So the standard level of documentation for a space mission would take way too long for our mission timeline. But on the other hand, having too little documentation makes it difficult to track down problems. And specifically for GT1, we made a documentation mistake that was filed early in the mission. We only discovered it somewhat recently, and this is also an active problem that we're working and may risk the launch slipping. So for GT1, we prioritized procedural and test documentation over technical manuals or design documentation. The procedural and test documentation is really imperative just to make sure that that you really are testing everything that you need to. But on the other hand, for technical manuals and design documentation, if the design is simple enough and you have open communication channels between the people using the design and the designer, like we had on GT1, then you really don't need highly detailed technical manuals. And some people don't read manuals anyways, so as the designer, you'll be getting lots of questions anyways, and that saved us time on GT1, not having to write all that. But what did help us time and time again was taking lots of pictures while executing procedures, especially when integrating the spacecraft. Taking a ridiculous amount of pictures so that from many different angles really helps to debug problems later on once the satellite is fully assembled. And I would like to talk about how we chose electronics components for GT1 using the careful COTS method. And for those of you who aren't familiar with the acronym, COTS stands for commercial off the shelf. And these are components that you can buy from multiple different distributors that are widely available, unlike the very specialty space grade components and expensive space grade components that may be more traditional for a space mission. And one of the principles of this approach is to use components that are inherently radiation tolerant by their architecture. So, for example, using bipolar junction transistors over field effect transistors or FETs where possible. And also to heavily derate your component. So you want to choose components that are rated for a condition much higher than your expected condition in your design. So your current maximum or power dissipation rating on your component, you want to make that much higher than what you expect. Additionally, many commercial components also offer an automotive grade or enhanced product option. And these are tested to more extreme conditions like larger operating temperature ranges and sometimes vibration than the regular commercial grade version. And they're only a little bit more expensive, unlike the space grade versions that may be many tens or hundreds of times more expensive than the commercial components. So usually those are worth buying for a CubeSat mission. Okay, so here are some things I think we can learn from the GT1 avionics development. So choosing a flight computer with good community support is very important, especially for the flight software team getting their code up and running as soon as possible. Making a functional test program as early as possible in the testing phase will make it very much easier to validate that the spacecraft is working correctly, and you'll be able to catch problems much faster. Focusing on the critical systems first, and for GT1, that was the flight computer, radio, and electrical power system. And we neglected the radio until late in the process, so that really hurt us. It's important to really focus in on the critical system. And designing with the careful COTS method, so that your design will work in the space environment, but with minimal cost. If we fix all the problems, current problems that we're having on GT1, it will hopefully launch aboard NG-16 into low Earth orbit this summer. So I'm very excited for that. And the GT2 mission has already begun. We're beginning the design process now, and I'm excited that I'll be also working on GT2 to improve the performance of the electronics, fix all of the annoying features on GT1, and actually realize our goal of making a high performance 1U CubeSat bus. All right, that's it for me. If there's any questions, please fire away.
Thank you, Andrew. So if you have questions, please go ahead and mute yourself and ask Andrew directly. Okay, so I didn't hear any question, but I have one, Andrew. So this seems a very exciting project, and it become to be very popular nowadays. And what is the most difficult part when you work on this project in your based on your experience?
Yes, so I would say the most difficult part is designing the tests and procedures. I would say that's actually perhaps more difficult than the actual design of the spacecraft. And that was very apparent to me when I when I started working in the lab, coming from a background of being an electronics hobbyist where, there's very little testing on your projects. You kind of just, put your project together and then see if it all works. And, if it doesn't, then it's a very laborious process of going through and figuring out exactly where you went wrong. But on a space mission, you want to test each system separately in any possible case. And then you have to do all that testing again once you integrate the whole system so that it's much easier to track down problems as they arise. So I would say that the testing and writing the test procedures specifically is the hardest part, for sure.
All right, thank you very much. Next presentation. Thank you.
By the way, can I ask a question?
Yeah, go ahead.
Okay, I have a couple questions if you don't mind. So for the GT1, is there any deorbit plane you're going to use passive or active deorbit control? The second question is, did you create a mass equipment list or power equipment list for the spacecraft or the avionics subsystems? And the last question is, did you perform the cost analysis on the spacecraft?
Yeah, so for the first one, the deorbit is passive. We expect in our orbital altitude and just the altitude that we're going to, we expect roughly a 6-month mission time before the satellite naturally deorbits. Could you repeat the second question?
Oh, thanks. The second question is, did you create mass equipment list, power equipment list for the subsystem?
Are you talking about like a mass or power budget?
It's an equipment list. If you don't use it, that's fine. So how do you manage the power consumption?
Yes, so our spacecraft in sunlight is incredibly power positive because of the deployable solar panels. We have much greater solar panel area than a normal 1U CubeSat, and we monitor the power consumed by the major power consumers, the flight computer, radio, and we also monitor each solar cell input string power on the spacecraft. So we can see if a component is taking up too much power, and we have control to turn on and off all the major components to save power as well.
I had a question.
Yeah.
Oh, can you hear me?
I can.
Okay, cool. All right. My microphone wasn't working earlier. You kind of somewhat touched on it, but I'm assuming this is a relatively low power source. So how did you approach keeping the satellite in the correct orientation to receive and transmit radio signal?
Yes, so our radio antenna is actually designed to be largely omnidirectional. So it should work if the satellite is in any orientation relative to the ground. We do have a attitude control on GT1, specifically a detumbler with magnetorquers. So that will help reduce the spin, because as we exit the deployer tube, the spacecraft will be spinning slightly. So we want to null out that rotation. But even if it is rotating, the antenna is designed to work in any orientation. And we get away with that because it's a very low data rate link. It's 9,600 baud or bits per second. So it's a very low data rate UHF radio link. So we can get away with having an omnidirectional antenna with our transmit power. Yeah.
Okay, thank you.
Mm-hmm.
I have a question. Can you hear me?
I can.
Yeah, thank you for the presentation. So my question is, what is the process to get a spot for the CubeSat into a launcher? Because you said maybe you wouldn't end up succeeding in fixing everything before it's launched. So is it replaced by something else, or?
Yes, so the process that we're using for GT1 is a ride share. So we have a contract with a rideshare company called Spaceflight Inc., which is going to integrate our payload, our 1U CubeSat, into a deployer tube that will have other CubeSats in it. And they really determine what launch we're going to be on, and we have compatibility to launch on different launch vehicles. So that means launching at different times. So if the launch does slip beyond this summer, then we have more launch opportunities even later this year.
All right, thank you.
Okay, thank you everybody, and thank you Andrew again. Let's move to the next presenter. So Jerry, are you online? Okay, I see Jerry's presentation. Okay, please go ahead. Oh, sorry, let me introduce you, I forgot. Okay, everybody, so next we have Jerry Hu to present for us. And Jerry is a senior AE undergraduate, and his research interest is in systems engineering and design. This semester is his third semester doing research with ASDL's model-based system engineering team. So let's have Jerry. Jerry, we couldn't hear you. Seems like you are muted. I'm trying to unmute you. And on my side showing you are unmuted, but we couldn't hear you. No, we couldn't hear you. Nothing.
Hello?
Oh yeah, now it's good.
Okay, you can hear me now, right?
Yeah, go ahead.
Okay. All right. So thank you for the introduction, Dr. Sun. So professors, fellow students, YouTube and Twitch TV greetings. My name is Jerry Su, and I'll be presenting requirements engineering focused system modeling of an unmanned lunar mission. So before I begin, I'd like to present the following quote by British statistician George E.P. Box, who states that all models are wrong, but some are useful. Whether or not you agree with the statement, one thing is certain. The accuracy of a model and its ability to represent a real-life system or phenomena is imperative to the success of the model. This begs the question, is model-based systems engineering a useful model? The simple answer to this is yes. The long, complex, and technical answer to this is also yes. Let me explain. The strength of MBSE is that it can be used in lieu of traditional, disparate forms of documentation. You have one unified system that has the capability to capture most, if not all, aspects of the project. It can be used to easily define how each component of a complex system is related, and can be a cost-effective method to save on both time and budget during the initial systems design process, allowing for implementation of alternatives without starting entirely from scratch. The framework also allows for traceability and downstream flow of requirements and constraints, which is one of the most crucial aspects of system design. Last and not least, it is a quick and easy way to generate documentation. To implement model-based systems engineering, we use the system modeling language in Magic Draw, the modeling tool of choice. This is currently my third semester doing model-based systems engineering. The first semester of the research was mostly learning best practices, and we modeled the Apollo command and service modules as part of a team project practice. The second semester of research was broken down into two parts. The first half was a series of training exercises centered around Colorado's Breckenridge Ski Resort that helped us gain fluency. We had free reign for the second half, and so I decided to partake in a systems engineer role in my concurrent space systems senior design course and co-modeled a system with the other systems engineer on the team. My approach to modeling the system was with a requirements engineering focus. The most important objective of requirements engineering is to scope, define, and to maintain the requirements pertaining to the system. This is often the first step that is done before any actual design work begins. There are 6 main activities in requirements engineering: requirements elicitation, requirements analysis, systems modeling, requirements specification, requirements validation, and requirements management. It should be noted that although these activities follow this general order and people take it chronologically, interleaving happens pretty often. And so oftentimes you have to reiterate or go back and fix a certain process. And so this doesn't necessarily have to be a chronological process. So moving on to the actual project, here is the concept of operations or CONOPS for the characterization of the exosphere from low lunar orbit to the surface, or CHELOS for short. CHELOS is a mission to characterize the density, structure, and molecular or charge composition of the low-altitude exosphere and dust environment on the moon, to better inform scientists and engineers prior to continued lunar and planetary body exploration. So here's a brief overview of CHELOS. CHELOS launches as part of a rideshare and circularizes its orbit around the moon. Over select locations, CHELOS will burn to a suborbital trajectory, release one of 3 probes that will undergo descent without active control, collecting atmospheric, dust, and charge data on the way down. The orbiter then burns to re-enter its original orbit, then continues the cycle until mission termination. Of course, that is the general concept developed after scoping, figuring out objectives, and a lot of trial and error. Before developing a CONOPS, a systems engineer has to first come up with the requirements that will help shape and define the mission design and system architecture. It is crucial to first obtain the constraints and customer requirements, as they will help constrain the design and will shape the direction of the mission. Then you ask the question, what does your system seek to achieve? You develop goals and objectives for your mission. Next, you delegate work, hire the necessary people, and designate experts to work on the different aspects of the mission, creating the work breakdown structure. The definition of the requirements is split into 2 parts, key and driving requirements. Some examples of key requirements are the budget, operation, orbit requirements. For driving requirements, you have command data handling, communications, DNC, power, propulsion, structure, thermal, etc. These will be discussed later. Deriving constraints from the request for proposal is fairly straightforward. Most requirements are explicitly stated in the requirements section of the RFP. It should look something, if you look at the top set of images, like requirement J3, for example. Sometimes the requirements or constraints are not included, however, in the constraints section. So it is important when you're reading the RFP to scrutinize it when scoping for requirements. And if you look at the implicit requirements section, I highlighted, small example that they gave, which is no hydrazine or radioactive material. And so you can derive 2 requirements from this, which is RTG prohibition and hydrazine prohibition. And here is a list of the RFP-derived requirements in table form. And this is the same set of requirements represented in a requirements diagram or in a requirements package form. Generally, different representations of the system should make it easier to understand, as multiple methods could be used. But keep in mind that too much redundancy creates clutter, so balance is very important. And here is an example of representation of the relationships between top-level objectives, scientific objectives, and the measurement requirements of the mission. To simplify this diagram, let's focus on the rightmost secondary objective 3 for the moment. So if you take everything out, zoom in, these requirements and objectives are represented in what is called a block definition diagram, or a BDD. The arrows show that each lower level requirement is derived from a level above itself. At the end of the chain, the measurement requirements are allocated to the instrument. And so the systems engineer is also responsible for defining relationships on the personnel side of the mission. So here is the work breakdown structure of CHELOS, with each role assigned at least two people for redundancy and workload purposes. My roles are highlighted in yellow. So I'm the project systems engineer 2 and the science payload engineer 2. A brief discussion on the difference between key and driving requirements. So key requirements are mostly higher level. They're mostly mission critical requirements and are often science goals or mission parameters. Driving requirements, on the other hand, are often lower level and impact the design or the spec of the design. So here we have an example of the key requirements, and in this case, the operational requirements. This is one example where the diagram's full representation of the requirements can indeed look a little cluttered. So if you clean up the text and consolidate some requirements and simplify stuff, you result in the following. Removing the requirement ID numbering and text reveals a much cleaner view of the relationships of the driving requirements, of the key requirements. The mission statement derives 2 additional requirements, requiring both an operational and ground network. Deep space network access derives 2 requirements as well, and it needs to be able to be accessed by the ground network, and operations is subject to its availability. Rideshare requirements of the launch vehicle constrain the orbit design, and the mission needs to have a launch delay window of 9 months. The secondary objective creates database requirements, and the mission is required to last at least 1 year. So now, moving on to the orbit requirements. They aren't as complex compared to the previous requirements, but if you focus on the most important requirements and simplify things, focus on the most important requirements, you get a simple diagram. And here it has a periapsis set at 8 kilometers derived from primary objective 1, and a secondary objective that derives a requirement for deployment of the probes. So here we have the driving requirements for command and data handling. And so the most important requirements for command and data handling are as follows. Derived from the operation network requirements, the health reports for subsystems are required. Derived from primary objective and the deep space network access requirement is a requirement to ensure at least 5.4 gigabytes of data storage between uplink windows. And derived from autonomous probe deployment requirements is the requirement for the CDH to serve as a real-time processor for the altitude determination and control. And moving on to communications requirements. Here you can see starting to have more and more interdependencies on different requirements, and this will result in a lot of requirements being derived from other subsystems as well. And so here you can see when you clean things up a bit, the communication subsystem communicates with the operation network and maintains ground communication, and therefore the requirements are derived from each respective subsystem. The general gist is that the more a subsystem is interdependent on other subsystems, or the more it interacts, the more its requirements will be derived from the other subsystems. And here you have the guidance, navigation, and control, or the GNC. And as you can see, it's also fairly cluttered. So if we focus on some of the more important requirements, we get this. Like the communication subsystem, the guidance, navigation, and control is crucial, and its operation depends on many other subsystems. Orbital positioning will affect its ability to localize itself. Its target altitude depends on the primary objectives. It has to report its orbital positioning to the ground network. And most importantly, to communicate and receive commands, it has to be able to autonomously maintain its orbit due to the limited DSN access. And here you can just, logically flow these requirements down, and you can kind of get a gist from where they come from. And here we have the power driving requirements. And so cleaning things up and focusing on some of the more important requirements you get the RTG prohibition that flows directly from the RFP as a constraint. The power necessary depends on the mode of operation, and it's specified in the requirements for the science and propulsion modes, respectively. So now moving on to the propulsion subsystem. The propulsion subsystem has its use of hydrazine contained by the RFP requirements. The delta V budget requirement was derived from the requirement for a low periapsis, which was necessary as it is where the probes are deployed, hence derivation from primary objective 1. The transfer orbit derives the requirement for lunar injection. The mission requirement of 1 year and full mission duration calls for a requirement of 10% additional margin for propellant. And the structure at first glance is subject to 4 constraints. The requirements legend, it's a little bit small on the top right, but from the color, the orange reddish shading, you can kind of see the requirements, and here it has 4. And so when you consolidate the requirements and highlighting the important ones, we have the obvious mass and volume. Oops. Sorry about that. We have the obvious mass and volume requirements derived from the RFP constraints. The rideshare and adapter constraints derive from the derive these structures ESPA if that's your requirement. As the system is deployed via rideshare, it needs to be able to withstand the G-forces experienced by the rideshare vehicle, hence the 6G load requirement. The thermal subsystem also is required to not use radioactive materials, and this is also derived from the RFPU constraints. The thermal subsystem was required to maintain the spacecraft components at 5% of the operational thermal range. And so if you take all of the objectives of this mission, we can obtain this diagram that shows the hierarchy and the flow of requirements. As you can see, all requirements are traceable and can be tracked for later verification and validation purposes. And here's the same done for the subsystem requirements, and the traceability and flow of the requirements can also be seen. And if you throw together all the requirements, we get this table, right? Which is fine for bookkeeping, but is not exactly enjoyable to sift through compared to those diagrams. And I understand it's a little bit small, but if you look, so these are, this is one single table, it's split into two, and it's cut down the middle. And if you look starting, if you count from the left, the third column is where each requirement is derived from. And the column on the right is what it's verified by. And so if you can create a table like this, it's very easy to see what the relationship each requirement has with different requirements or what it's verified by, and it's very easy to check. So now moving forward, we want to talk about verification and validation integration. So as the focus of this project was mostly requirements engineering focused, much of this work done was in the refinement and derivation of the requirements needed to set up the system's design process. However, much of the computational work done was done outside of Magic Draw. And the delta V calculations were done in MATLAB and STK, and spacecraft mass and volume calculations were from SolidWorks or from literature. And so the input and outputs of the computations and simulations could still technically be documented in Excel. You can output what you calculate in MATLAB and then put it on an Excel file and then take it as an input and then put it back into Magic Draw. But this kind of defeats the purpose of model-based systems engineering because you want to cut down on that documentation that's spread out. And so the next steps for refining this model would be to include parametric models that integrate, for example, the delta V computations or SolidWorks mass and volume constraints and calculations into Magic Draw for the automatic reiteration of each design change or for certain alterations to values, and it would compute automatically. This would not only speed up any tweaks and alternatives, but also allow for the automatic system validation through a dashboard that could indicate if requirements are met. And so this pretty much summarizes what I've done so far. Do you guys have any questions?
Thank you very much, Jerry. Any
Thank you.
questions, Jerry?
I have a question. So is this like a continuation of what you did in your senior design project?
Oh yeah, so this is a combination of my senior design project, but I applied my systems engineering research to it as a foundation for me to start from a very requirements engineering focused perspective.
Okay. Thank you.
Yeah.
Hey, Jerry, I have a question. How do you account for other requirements that aren't included in the RFP? So maybe you have some sort of limitations in your available resources, like maybe like testing facilities and those sorts of things. Is that something you would include in like a model-based system engineering model? And like kind of how would those requirements flow down?
Yeah, that's a very good question. So, for example, if you have delays in your schedule, or if you have something that was unforeseen, it wasn't. I had this in my supplement slides, but I had an example of what a fabrication schedule would look like, and there are obviously margins inside fabrication for different phases, and even according to the RFP, you had to have a 9-month launch window, and so there was a lot of extra time allocated for budget concerns or for the under delivery of scientific instruments, for example, and so within a certain reasonable margin, these would be accounted for. Yes. And so far, I have to be honest, this schedule was created in Excel, and I'm still looking for a way to create a readable schedule in Magic Draw, and I'm pretty sure there's a plugin for that, but I'm still looking into it. I hope that answers your question.
Thanks.
You're welcome.
Are there any other questions? Okay, let's thank Jerry one more time. Thank you, Jerry.
Thank you.